Go ahead, please, Yueqing.
Hi, I'm Yueqing Chang from University of Illinois. Today I want to present my preliminary results I got from first principles study of the phonons and crystal electric field excitations on this material, cerium sesquioxide. Our experimental collaborators did this Raman scattering experiment on cerium sesquioxide, and they found there are two emergent collective modes appear during the Neal transition of this material. So on the left-hand side, we have the intensity versus energy plot. So different colors stands for different temperatures. The Neal temperature for this material is 6.2 Kelvin. And on this plot, you can see there are 4 peaks. The second peak is the 2 phonon band, and the third one is the crystal electric field excitation peak. From now on, I'm going to use the acronym CEF for crystal electric field excitations. And what's on the left and rightmost are omega-1 and omega-2 peaks. These 2 peaks only occur during the phase transition. And on the right-hand side, we have this panel where they plotted the positions of all these 4 peaks. The y-axis denotes the energy, and the x-axis is the temperature, and the dashed line is the Neal temperature. On the left-hand side, you have the AFM state. On the right, you have PM state. So you see that omega-1 and omega-2 only appear during this PM to AFM phase transition. A natural question would be, what are this omega-1 and omega-2, and what is the underlying mechanism behind these two collective modes? So one may ask, what are the possible coupling channels that could exist in this material? The first one is the magneto-phonon coupling, which is basically saying that you can have new phonon modes when the material has different magnetic texture. So for this one, we computed the phonon modes in different magnetic states, AFM and FM, using density functional theory with LDA plus U plus Manova coupling. And also we can have electron phonon coupling, which also gives rise to the CEF phonon coupling. For this one, we compute the CEF excitation energies and also the electron phonon coupling constants. We depopulate the F electrons in the material, so there are no interactions among the F orbitals. And then we can just conveniently extract the differences between the F orbitals as the CEF excitation energies. And lastly, we can have this magneto-CEF coupling, which needs strongly correlated methods to address. So for today's talk, I'm going to focus on the first 2 coupling channels. Here's another intensity versus energy plot. The gray curve is the original Raman spectrum when temperature is 4.1 Kelvin and the material is in AFM state. And the orange lines are what I computed as the Raman active phonons when the material is in AFM. So you see that these four lines corresponds to EG, A1G, and A1G plus EG modes. Our results agree with their experimental measurements pretty well, maybe off by about 20 centimeter inverse, but that's only about 2 millieV. And down below, we have the schematic plots for all these phonon modes. You will see that EG modes correspond to cerium and oxygen atoms moving in the XY plane, and the A1G modes corresponds to the atoms moving in the Z direction. Here I'm plotting the Raman active and inactive modes on the same plot for FM and AFM states. So the orange dot stands for Raman active and the blue dot stands for Raman inactive. You can see that during the phase transition, only the Raman inactive modes move. And when you compare this with the experimental results show that the omega-1 is on the left-hand side of the 2 phonon band, which is a very phonon-like mode. But for our results, we only see a Raman inactive move. So this suggests that this omega-1 could not be due to simple change of magnetic states. A second coupling channel that we want to discuss is the CEF phonon coupling. Here I'm plotting the energies of the 2 electronic states, epsilon-1 and epsilon-2, as a function of the atomic positions. So you will see that epsilon 1 and epsilon 2 depends linearly on the atomic displacements away from their equilibrium positions. If you subtract epsilon 2 by epsilon 1, you will get the CEF energy, also plotted against the atomic displacements. And the slopes of these three curves are electron phonon coupling constants for states 1 and states 2. And down below, the slope of this curve is going to be the CEF phonon coupling constant. From these two plots, you can see that CEF is coupled strongly to this phonon mode A1G. Here I'm showing you the CEF phonon coupling distribution for different Raman active modes. So the upper panel is just a distribution. The x-axis denotes the phonon frequencies, and the y-axis is the CEF phonon coupling strength in centimeter inverse. And here I'm showing you EG, which is this peak, A1G, which is that right peak, and on the right most you have A1G and EG mode. You will see that all these distributions, most of them are centered around 0 centimeter inverse. But if you take the weighted average, you will see that A1G and EG mode and the rightmost EG mode couple strongest to this CEF mode. And for our model, we want to discuss mainly this A1G mode because energetically it is closest to the CEF peak. On the right-hand side, I'm showing you the second quantized Hamiltonian I'm using for this electron phonon coupling. So the first two terms are just the electronic Hamiltonian. C1 dagger C1 and C2 dagger C2 are the creation and annihilation operators for electronic states 1 and 2. Epsilon 1, epsilon 2 are their energies. And the second term is the harmonic phonon Hamiltonian. And the last two terms are what we call as the first order electron phonon coupling terms. And lambda 1, lambda 2 are just the slopes of what I showed previously on the last page as the electron phonon coupling strength. If we don't have electron phonon coupling at all, you will have this CEF energy distribution. But after we include this electron phonon coupling, you will see that CEF peaks are broadened, and the overall profile will be moving to the higher energy by about 7.5 centimeter inverse. If you compare this with the experimental results, which is on the right-hand side, they have this CEF peak when the material is in AFM state that has a higher energy for about 10 centimeter inverse. Another thing I want to point out is that our DFT calculations generate broader CEF peaks than their experiments. To summarize, for today's talk, I introduced these two emergent collective modes that appear during the neo phase transition of serious sp oxide. And we use DFT to calculate the phonon modes for the material in FM and AFM states. We show that only Raman inactive modes would move during the magnetic phase transition. We also show that electron phonon coupling could broaden the CEF peak and move the overall CEF peak to the right-hand side to the higher energy by about 7.5 centimeter inverse. So for this question, during the PM to AFM phase transition, we have probed the magneto-phonon coupling branch. We show that new phonon in Raman could not be due to simple change of magnetic texture. We also looked at the CEF phonon coupling and show that CEF could move due to the electron phonon coupling, but we still haven't explained the new vibrational mode omega 1. In the future, we want to discuss the magneto-CEF coupling using the strongly correlated methods. And we also want to see whether this magneto-CEF coupling could give rise to new vibrational mode. With that, I'd like to finish my talk and thank you for your attention.
Questions?
So why is it that you need strongly correlated methods to probe the magneto-CEF coupling?
Because for this material, it's a material with F electrons, and if you want to look at very precisely how the magnons how the phonons behave, and also how the magnetic texture could change the CEF peaks, I think you would need strongly correlated methods to describe those.
Others?
I think I may have one. It's kind of simple, but I think it's just referring back to your Hamiltonian that you use. Yeah. So like electronic states 1 and 2, are those referring to the essentially the states at omega 1 and omega 2?
Not exactly. So electronic states 1 and 2 are the two electronic states that are involved in the CEF transition.
Okay.
So basically, if you have one electron previously in state 1, and now it jumps to state 2 and creates a hole in state 1, and that energy difference is what we want to compute is the CEF excitation energy.
Okay.
One more? You did the calculation of those levels by depopulating the f orbitals.
Yes.
Would you have gotten? Would you be able to do the calculation by putting the f electron in and putting it in one orbital and putting it in the other orbital and comparing the two calculations?
Technically, yes. You could use constraint DFT to do that. So with constraint DFT, you can like constrain the ground state, L or M, and then you can just force one electron to occupy some F orbital, and then you do the whole overall DFT calculations and SCF, and then got the ground state energy, and then you can force the ground state to have another L and M, and the difference between those two ground state energies is going to be the CEF energy.
And would it be the same as the one that you got?
I haven't tried that way yet, but I believe it should be similar to that.
Okay, well, thank you very much, Yueqing, for an excellent talk.